Welcome back. Sorry it took so long, but we are going to hop right into it. So, what are number bases? Well, number bases are another way, or kind of the idea of representing numbers. So, let's say a number 386. Now, you kind of intuitively know this number because you've grown up with it your whole life. And this represents, what it really represents is it represents 3 times 10 squared plus 8 times 10 plus 6. I probably should say 10 to the first power times 6 to the 0th power. So this is what it actually represents, it means to have a number 386. It represents that these are essentially coefficients and of describing these numbers. So there's 3 of 10 squared, 8 of 10 to the first powers, and 6 of 10 to the 0th powers. And so that's what it actually means to have a base. The base are these numbers that are being increased in powers. And obviously this continues, like if we were to have, and then you do plus, let's say 3 times 10 to the negative 1 plus 6 times 10 to the negative 2. It continues. And so, well, obviously this isn't 386 anymore, but the bases are those numbers that are being, raised by certain power. So if you had, let's say, base, what's a convenient one? Base 6, right? Or let's say base 4. That would mean that you would have, 3 times, you do, 4 squared. Well, actually, example 386, 3 times 4 squared plus 8 times, well, you won't have 8, but if you had a number, let's say 332, so 3 times 4 squared plus 3 times 4 plus 2 times 4 to the 0, and this obviously to the 1. And so that's, the base is the thing that is being represented by these coefficients. It's what it means to be in a certain place of that number. To be in this is considered the 0th place, the 1st place, the 2nd place. To be in the 2nd place means that you're representing a certain amount of the 4's squared. And so that's really cool. And so you can do this with a lot of bases. And I'm going to cover really quickly two popular bases is so you have binary. Actually, before I go into that, I need to discuss a very important topic. Let's say you have base 7. Let's call it B7. Maybe let's say base. What's a good number? Base 3. Now, or I like base 5. Let's do base 5. Now, actually 6. Let's do 6. So, what's very important is that, okay, sorry, I keep changing it, but I think I'm gonna do 9. What's very important is that the base also indicates to what number you can't represent. So, for example, for base 9, you would have, and for any number, you would a times, let's start with 9 squared plus b times 9 to the 1st power plus c times 9 to the 0th power. So these coefficients, and this would be the digit a, b, c in base 9, these represent the amount of these. And so let's say you had a number, let's say, 188. Looking pretty good. Let's say you add 1 to it. Now you might say this would be 189, and this is in base 9. You might say it's 189. But the issue with that is now if we represent it in base 9, that will be 1 times 9 squared plus 8 times 9. 8 times 9 plus 9 times 9 to the power of 0. Now, this, well, actually, wait, we just do 9 times 1. This conveys the number of 9s, right? Because this digit is 9. And so whatever this is, it's a multiple of 9. But this number is supposed to be counting the number of 9s. So you can't represent this as 9. Well, you could, but it's more efficient to just use, if this is 9, this gets converted up into here. So actually, I realized I made it a bit complicated. So if we do 178, or well, let's do 148. When you add 1 to it, now you can't represent this group as like a certain, so 9 times 9 to the power of 0, because this has a certain amount of 9s in it. It's multiple of 9s. And so, but this over here is tracking the multiple of 9s. And so you use that one. And so this increases by 1 because there's one more 9. And so it's 150, actually, instead of 149. And this applies, for example, the trickier example is with 188. It's 188 plus 1, right? So this carries over because you can't go to 9 because this then represents 1, 9, which this is used to represent. And so now you have 9 9s, but this represents, which is 9 squared, but this represents the number of 9 squareds. And so you just added one number of 9 squareds, and so it should be 200. And so that's one nuance is the number of the base you use digits 1 less than that. So for example, for base n, you use digits 1 to n minus 1. Well, like 1 to n minus 1. And so those are the digits that you use. Because when you get to n, then that it's a certain multiple of that n, and the next placeholder up represents, let's say n squared, and so you've just created n squared. Cool. Okay. So now we're going to go into useful ones. So binary is a very useful one, and it's base 2. So the only digits, you can use the formula here, the only digits you can use is 2 minus 1 or 1. Well, actually, sorry, I should say not, it should be 0 to n minus 1. So you can use, you can use 0 to 1. And so that's very limited. But that's the idea behind binary, because it's used in computers, because computers use electrons, which have 2 states of off and on, which can be represented as 2 things, 0 and 1. And so that's what's actually used to carry information in binary. Another one is hexadecimal, which is base 16, and it's used to represent colors. Now, base 16 is very special, right? Because that means it goes after 9, there's a certain thing that has to represent the idea of 10, but you can't use 10, because 10 is using 2 placeholders to represent, one value, which is, it's in base 10, and so it's obviously uses digits 0 through 9, and so you can't go past 10, because then you violate the further counting of 10. And so actually use A to represent the idea of 10, right? The idea of the value of 10. And you go ... up to the idea of 16, which is, well, actually, no, you don't use 16, you use 0 to 15, but F is that idea of 15, if you kind of get what I'm saying, by it conveys that value, but it doesn't use 15 because 15 has 2 placeholders, right? This is not, because each placeholder represents values relating to 16, certain power 16. And so, quick example, 9AB, actually that's difficult to compute. Let's say 9B would represent, let's do AA. AA represents, 10, A is 10, so represents 10 times 16 plus 10 times 16 to the 0. So this represents 160 plus 10, which is equal to 170. So, whoa, where did I go? So 170 so AA is equal to base 16AA is represented by base 10 170. Cool. So yeah, that's pretty cool. And the reason it's used to represent colors is because colors has 3 values. It has red, green. Actually, you know what? Pretty cool. Here, I'll do red, green, and where's the blue? And blue. It has 3 values. And what they do is they span from 0 to 255. So they all have values of 0 to 255. But 255, you might see, is very close to 16 squared, which is equal to 256. And so actually what you can do is you can represent 255 as very close to 16. So it won't have a third placeholder because 16 squared represents third placeholder, but it will have a second. And 255 in base 10 is congruent to, congruent means like basically the same as FF in hexadecimal. And so you can neatly represent red, green, and blue values as FF, or well, I guess 00 to FF very neatly. And so that's cool. And FF represents, 255, and so that's all of that color. So if you have the value of FF0000, that means for these values, the green and blue values are 0, but the red is full. And so this color is actually, what we call red. Cool. And so those are some of the uses of bases. And quickly, I'll go over some cool cases where we have let's say we'll start with just irrational powers. Irrational bases. Now this seems crazy, but let's start with square root of 2. Now, the powers of square root of 2, let's write them out because this is what is conveyed by a base square root of 2 number. So, this is getting a bit sloppy. Anyway, what you can see is that the even powers, so this one, this one, this one, and this one, all have real numbers. Because, you can write them, even means you can write the number as like 2k. And so you can write to the n. So you can write this as square root of 2 times 2 to the power of n. And so this is always 2, and so it's always 2 to the power of n, which is a real number for real values of n. And so those represent real powers. And more specifically, it's very similar to base 2 in that it represents, for this term, it represents the base 2 system of 2 to the power of 1. This represents the base 2 system to the power of 2. And so on. It's base 2 system to the power of 3. And so for any square root of 2 times 2n, right, even number, it just represents 2 to the power of n. So that's cool. And so what you can do is, like, if you want to represent, so let's say like the value 111 in terms of base 2. Actually, wait, hold up, that'll be a lot. Let's just do 8. Well, okay, let's do 7 in the power of base 2. Now, what you can do is, that this base square root of 2 system is the same thing as base 2, but, and this represents 2, 0. Base 2 is basically the same thing, but on almost like a leap. You go leap from these, leap to these. And because these ones represent irrational powers, which is not, you can't have irrational power with the real number, representing real number. So actually, base 7, you would compute what base 7 and base 2 is, and that would be 1, 1, 1. So what you could do is you could represent that in base 2, square root of 2, as, so base square root 2, as, you can do 1, 0, 1, 0, 1. Because all this is base 2 is essentially woven into the base square root of 2, but you have the 0 values for irrational values, and otherwise you have just base square root of 2. And so that goes for any irrational, well, any like square root irrational base. So that's cool. And then a quick other one is fractional bases, which is basically, let's say, like 1/3. What this actually is 1/3 is written as 3 to the negative 1. So it's essentially raising 3 to the negative 1 powers to positive powers. And so if you write the powers out, you can say, so 3 to the power of 0, well, you're raising 3 to the power of negative 1 to certain things. So to the power of 0, 3 to the negative 1 to the power of 1. Well, it will go this way. So this would be opposite direction. So to the negative 1, 1 to negative 2, ... So 3 to the power of negative 1 to the power of negative 3. And then this would be positive. So 3 to the power of negative 1 to the power of 1. And then I'll just complete this for full understanding. And then 3 to the power of negative 1 to the power of 3. And so actually what this would be is these powers, because, a to the b raised to the power of m is equal to a to the power of bm. And so since these are two negative numbers, these will make positive numbers. And then since these is negative times positive, these will make negative. And so you actually get the result of this being, 3 to the power of 0, 3 to the power of 1, 3 to the power of 2, 3 to the power of 3, and this would be 3 to the power of negative 1, 3 to the power of negative 2, 3 to the power of negative 3. And so actually, as you advance up in the base 1/3 system, you're actually doing the same thing in base 3 system, but actually going down. And so essentially, what you can see is the base 3 system is, I'll write so the base 3 system would be, this would be what it is. And so you can see that the fraction is actually flipped. So in general, like 1 over n base is just like reverse of n base. And so that's really cool. And then obviously for like the digits to use in that case, you would use up to the digit in the denominator. And so that's really cool. And obviously for the digits for the irrational bases, you would use up to the digits in the square root. Or just any like irrational one. And so that's cool. So thank you so much, and I hope you have, I'll give you one problem actually. I want you to convert the hexadecimal values of, let's say, 3a times 46